Okay, there's Panda Bear in this because I just needed to cover something, so that was all it was. It is not relevant to stoichiometry or gas laws. All right.
Is it
Okay.
a bad word?
No, I just didn't want you to see the answer. All right. So, so just a quick review. We went over the ideal gas law over here. Okay. So we had this PV equals nRT. We rearranged it like crazy on Friday, and we also replaced this N with our little mass over molar mass. And then with that, we were able to come to this equation down here, the meow equals dirt over P, right? Okay. So what I want us to do is I actually want you to start with number 4, right there. That's the Panda Bear is covering it right now. There you go, number 4. And I want you to answer this, okay? So once again, the equation that you're basing it off of is meow dirt over P. And so what they're asking you is how is density, right? So how is this guy related to this one and this one? And then how is it related to temperature? Okay, so there's kind of like a pause right there, okay? So density varies, and your answer choices here are just directly or indirectly, okay? So what was something that I told you back on your notes on that first side? How do you know if something's a direct relationship when you have this big equation? It's over there on your left. If you just kind of look at your notes on the left, we wrote it, remember we said direct. We wrote it off to the side. There's something about the equal sign. Do you see it? No? What did you I see you pointing to something. Check marks, yeah, okay, so this is what you guys wrote down. For the direct, you wrote this, right? And then for the indirect, you wrote this. What that means, okay, is that if you have things on both sides of the equal sign, that is a direct relationship, okay? If you have things on the same side, that is an indirect relationship, okay? Furthermore, before you go in now, look at it, okay? I want you to also remember, Charles' law, was that a direct relationship or an indirect relationship? It was direct, right? So this was a direct. Boyle's law was a what? Indirect. So look at the positions of the variables as well. So using that idea, now I want you to answer the 2 questions, okay? Density varies blank with molar mass and pressure, and blank with the second blank is Kelvin. If you just want to put that in so you don't have to think about it. I wrote that lovely. Okay. Okay, so go ahead and try and think about which one's direct, which one's indirect, okay? Are we all good? All right, so density varies how with molar mass? What did you guys say? How does this relate to MW? It's direct because it's on both sides of your equal sign, if you see that, all right? So density varies directly with molar mass and pressure, okay? Why are we saying the pressure one? What is this relationship right here? Well, we know it's direct, but why are we saying that one's direct? Because they're what? They're one on top of the other, right? They're stacked. So that was something that we saw was a direct relationship. When they're next to each other, that's always indirect, right? So that leaves us with density now relating to temperature. They're on the same side of the equal sign. So this is going to be an indirect relationship. And I want you guys to be ready for test questions kind of like that, okay? Are there any questions on figuring out relationships from equations? All good? Okay, so turn over your paper. You're on the next side. Okay, so what we're going to be getting into today is we're doing the kind of pre-work to stoichiometry for gas laws, all right? And if you remember, the first time you learned how to do stoichiometry, we had to teach you conversion. So we taught you what the mole was, and then we taught you to go from grams to moles, and then we taught you to go from grams to particles, right, using Avogadro's number. So that's all that you guys are going to be starting with today. However, these first couple bullet points are going through how we're going to associate them with coefficients later. So I just want you guys to be aware of that, all right? So for this first one, make sure it's big enough for me. All right. Gay-Lussac's law of gaseous volumes of gases. I'm sorry, combined. Oof, my bad. Combined volumes of gases states that at constant temperature and pressure, the volume of gaseous reactants and products can be expressed as ratios of small whole numbers. Okay? And where do we usually get that information from? What is that going to be? The small whole numbers that we usually use to find ratios. Your coefficients, yeah, good. Balance equation. All right, and so the example that they're giving us is just our typical hydrogen gas. Whoops, sorry. All right, so hydrogen gas, which will be your H2 diatomic, okay, plus O2 gives me H2O. And we know that we got to balance this. We have 2 oxygens on the left-hand side, so we need to make sure we have 2 on that side. Now we've changed our hydrogen to be 4, so we're going to put a 2 on that side, okay? So now it's balanced. So when we were first learning the beginning of stoichiometry, I kind of said, what is the mole ratio of this? And what would you guys tell me for this equation? It is a 2, 1, 2. Good. Okay, and so we know that that is 2 moles to 1 mole to 2 moles. Well, what we can now do is we can also put liters after those, okay? And so what we're relating is, what we're saying is that given those constant temperature and pressure, you're going to have the same volumes as well, all right? So that they're kind of relatable, and that's what I want you guys to get from this, okay? All right, so Avogadro's law okay, Avogadro's law is just going to state that equal volumes of gases at the same pressure and temperature contain equal numbers of molecules. Okay? So if we know this is directly related to the moles, how much does 1 mole contain of molecules? How many molecules does 1 mole contain? What's that magic number that we learned? Good. Good. 6.02 times 10 to the 23rd. That big Avogadro's number, right? So, so once again, this is just showing the 2, 1, 2. You can relate that to molecules as well. All right? It's a ratio. So it's not saying there's only 2 molecules. It's just saying the ratio is 2 to 1 to 2. Okay? All right? And we can kind of fill this guy in. This is what we had from that Pogel, where K was your constant and N was the number of moles of gas. Okay? So this is a version of Avogadro's law. That's what they're showing. Okay? All right. So enough about that. We're going to go into some of the math that you're going to use right away. We'll come back to using those coefficients more tomorrow. Okay, so you guys will do a little bit more on the stoichiometry side tomorrow. So, so starting with this, recall that 1 mole of a substance contains, how many particles did you guys just tell me? Good. You guys should have that one memorized by now, okay? So if you were not shouting that out, you need to get it back into your brain. Okay, 6.02 times 10 to the 23rd. So don't forget that when you go to type that into your calculator, that's actually 6.02 E23, right? Okay, also recall that molar mass states how many blank are in 1 mole. So what what do we want you to fill in right there? How many what? What? Grams. There you go. Okay. And this information we usually get from the periodic table. Right? So go ahead and look at your periodic table. What is the molar mass of sodium? Good. You don't get the next one. All right, so 22.99 grams per mole. Somebody figure out ammonia. We have nitrogen, which is what? So, what? All right, so you guys did the total, but so nitrogen was about 14, hydrogens are 1 each, so it's about 17 grams, okay? So 17 grams per mole, and that's very rounded, okay? All right, so you will be using your molar masses, so it's important for us to make sure we know how to write our different formulas, okay? That's where that's going to play an important role, okay? Any questions on this? This is the basic part, okay. So looking at the other side, okay, according to Avogadro's law, one mole of any gas will occupy the same volume as 1 mole of any other gas at the same temperature and pressure. So what they're saying is keeping those despite the mass differences, sorry. Okay, so what they're saying is as long as you have the temperature and pressure the same, and typically what the questions that you guys are going to see are the STP questions, then you can assume that 1 mole of a gas is going to occupy the same volume. And that's where our little transition to Volumeville, when we built our little stoichiometry land thing, that's where the 22.4 is going to come into play. All right, so standard molar volume of a gas is defined as the volume of 1 mole of gas at STP. So that's going to be important. So whenever you're reading your gas law questions and you see this, it's at STP, I want you to circle it so that you make sure you're looking for that. If it's not given to you like that, that's something to question, okay? You gotta make sure what conditions are you sitting at too. All right, so just remind me, what is the temperature? What is standard temperature? 0 degrees Celsius, which is what in Kelvin, you guys? All right, and standard pressure is what? What? 1 atm, there you go. Make sure you include those units. So anything equal to 1 atm. Good. All right. So it is a mole to volume conversion, basically. Which for you guys, I don't feel like that's a big deal because I didn't teach it to you guys that way. Make sure you're bringing your words down to the right to cancel them out. Okay, that'll be a big deal. What I do want you to note when we start doing the next problem, okay, is that there are shortcuts. And yes, I want you to use the shortcuts if you can. Otherwise, stick with what you know. Stick with what you do for stoichiometry and don't change it too much, okay? I always go the long way, so no shame in going the long way. But you will definitely see the shortcuts in here. All right, so as a conversion factor, we are saying that 1 mole of a gas is equal to 22.4 liters. Okay, and that's where our B 22.4 came from in our picture. Okay, so remember, we have Moletown in the middle. Okay, we had Volumeville over here, we had Particle City over here, and we had Graham Land over here. So remember, in order to go from volume to Particle City, we always have to go through that mole. What you're going to see in gas laws is that you can actually make that conversion directly across by just assuming the mole, all right? And that's what I want you guys to look for. But remember, that's your basic layout of your cities, okay? Your map. All right. So Looking at the first one, a chemical reaction produces 0.0680 moles of oxygen gas. All right, so before I keep going, what does oxygen gas look like? What is O2? There we go. All right, so I'm going to write that off to the side. And they gave me moles. That's cool. What volume in liters is occupied by this gas at STP? All right, circle STP. Make sure you know that it's in the question. As soon as they say that, now you can make those assumptions that we just wrote notes about. Okay? So, how do we start stoichiometry? How do we start any conversions? What number do we use? With the number that they give you, right. Okay, so you can say 0.0680. We're going to go ahead and label that. I know it's not important to have the labels when you're just doing conversions, but get in the habit of it again so that when you start switching characters again, you know what to do. All right, next step. Words down to the right. Good. So we're going to say mole of O2. What are we trying to convert into? Volume. Is there a conversion between moles and volume? Is there a conversion? Yeah. That's the B22.4. Okay? So we're going to say liters of O2. And we're going to fill in our numbers. The numbers are going to be 1 mole of O2 is how many liters? There we go. So this turns out to look like just straight multiplication. So go ahead and plug it in. We'll get our answer in a second. Okay, so you should have been getting what? Good, 1.52. What are my units? Liters O2. Okay. All right. So that was one of those one-steppers. So let's look at the next one. Let's see what we've got. And don't forget, always go back to your basics. If you don't know where to go back to your basics. Words down to the right, do a conversion. Words down to the right, do another conversion. Okay, don't forget that. All right, so this one says a chemical reaction produced 98 liters of sulfur dioxide. What is sulfur dioxide's chemical formula? What is sulfur? S. What does dioxide mean? How many oxygens? 2. There we go. All right. Gas at STP, circle it. What was the what was the mass in grams? So we want to get to grams of gas produced. So we're going to, once again, we're going to start with what they give us, which was the 98 liters of SO2. Make my railroad tracks. Next step, words down to the right. Is there a conversion between liters and grams? A direct relationship? No. Okay, no. You will see the shortcut in a second, but there is nothing there, right? So looking at our map, you cannot get from this guy over to this guy. Okay? So we're going to go through the who. Moles. No mole bridge in this one, actually. Remember, mole bridge is when we're trying to change characters, so it'll be when you're comparing two different things in a balanced equation. So right now, we're just doing conversions. It's the same character. All right, so let's fill in the numbers for this one, and then we'll keep going. So 1 mole of SO2 is 22.4 liters. That's our constant, okay? I'm going to continue my railroad tracks. Words are going to come down to the right again. And I know there's a conversion factor between moles and grams. So when we go to plug that in, we know 1 mole of something is its molar mass. So sulfur is 32, and oxygens are each 16. So it's 32 plus 32. What is that? There we go, 64-ish grams. Okay, plug that one in. So the way it'll look is multiply all the guys on the top and then divide by 22.4. And hopefully you're seeing your shortcut after this one. Okay, what did you guys get for that? 280? Yeah? All right, so let me point out the shortcut. It was this. The fact that you have a 1 mole on top and a 1 mole on bottom, is it necessary to go to the moles? No. All right, so as long as you understand that 22.4 liters is 1 mole and the molar mass is 1 mole, feel free to change this into a one-stepper where you just move that 64 over and you would have just had a shortened version, okay? Now, if that just kind of went over your head, please stick with the long way. That's what I do. I always go through my moles because it just makes more sense and I see things cancel out and it's pretty. So, okay? All right. So the last one, we're going to particle city on this one. Okay? So the last one is saying how many molecules, so that's one of those funky chemistry words, right, are contained in, which means what? What number are we going to be using for funky chemistry words? Avogadro's number, good. Are contained in 5 liters of NH3 at STP. I didn't mean to circle that. All right, so, by the way, who is NH3? Ammonia. No ammonium. That's NH4. All right, cool. So we're going to start with our 5 liters of ammonia. Words are going to come down and to the right. I'm going to go, there is not something that goes from liters to molecules. So I'm going to go back through moles. Okay, filling that in. I know 1 mole is 22.4 liters. I'm going to bring words down to the right again. I'm going to end with particles. Molecules. Whoopsie. Sorry. Okay, and I know 1 mole is equal to Avogadro's number, which is that 6.02 times 10 to the 23rd. I put E23. Okay, so type that in just to make sure you're getting the right answer. The answer is going to be 1.34 times 10 to the 23rd. And once again, you see a shortcut here. You don't have to put those moles. Okay? So type it in, make sure you've got it, and then you can flip the packet over to the practice that's on the other side. You've got at least 7 minutes to work through some of it. You can either do the multiple choice or you can do the short answers. So now you're going to work on this page, and I want you to get, I would say, at least 4 things done on this page before you guys are totally packing up. If you do this side, you have to do more than 4. But if you work through the problems, I'll have the key ready for tomorrow, and then we'll warm up with it. Okay? And that's it.